Hello everyone, my name is Pedro Ribeiro and I'll be presenting our work, Fruit Quality Control by Surface Analysis using a bio-inspired soft tactile sensor. Fruit and vegetable consumption has been steadily increasing during the last 2 decades, with consumer demands for quality rising while still maintaining a reasonable value. Nowadays, this market represents a significant portion of the agricultural product market, with a valuation of £2.2 billion in the United Kingdom. Tactile perception of fruit quality by touching or tapping is an important source of information for consumers in assessing the quality of a fruit product, ranking as the second most important factor in a survey of fruit consumers. When using force to estimate fruit quality, the magnet-stellar penetrometer is the established instrument of choice, providing the most accurate assessment of quality at the cost of destroying the tested sample. Recently, tactile sensing has been used to estimate fruit quality, reaching to classification accuracies of approximately 90%. However, only firmness of the fruit has been tested, with other tactile features that could provide important information about quality, such as surface texture, being neglected. In this work, we present a system using a hair-like tactile sensor, optimized for measuring small forces and textures to classify fruit quality through surface characteristics of the fruit. Due to its compactness, it is non-destructive and easy to implement on existing platforms. The sensor is composed by 3 parts. The cilia tactile sensor, which is a sensing element of our device, and it is connected to a support PCB that will provide the connection to the data acquisition board. The data acquisition board reads the analog signal from the sensor and converts it to a digital representation that is communicated to the computer. The sensing element itself is composed by a passive magnetic cilia, which will deform on contact and generate the magnetic signal that is read by the magnetic sensor die underneath. The magnetic sensor die is composed by a set of 2 by 20 micrometer squared sensing elements, themselves composed by a stack of thin metallic films. When a magnetic field is applied to the sensor, a variation in resistance is observed in these elements. This variation in resistance occurs due to the tunneling magnetoresistive effect, or TMR effect for short. Two groups of thin films with magnetic properties exist in the stack, separated by a thin 1.4 nanometer layer of aluminium oxide. The total height of this stack is 100 nanometers and is patterned into sensing elements of 2 by 20 micrometers squared. The top portion of the films were combined in such a way that the magnetization of these films is pinned, that is, the magnetization remains constant independently of the external magnetic field. On the bottom part, however, the magnetization of the films does rotate when a magnetic field is applied. When a current is applied to the stack, electrons will flow through it, crossing the insulating aluminium oxide thin film by quantum tunneling effect. The probability of an electron crossing this barrier is proportional to the angle between the magnetization directions of the free and pin portions of the stack, being maximum when the layers are antiparallel to one another and minimum when they are parallel. Macroscopically, this effect manifests itself as a variation in resistance of the TMR element, with a linear relation between applied magnetic field and resistance being observed. However, the measurement of a single element or array of elements is not easily integratable, as it requires the usage of a precision, variable voltage, constant current source. To facilitate integration with the robotic platform, the sensor die is produced using a Wheatstone bridge configuration. This configuration is achieved by combining sensing elements with anti-parallel sensitive directions. That is, some of the elements will present high resistance for low applied magnetic fields, while others present low resistance for low applied magnetic fields. When combined, as is presented in the schematic, a differential voltage can be measured in the bridge branches that will present a bipolar, zero-centered response to the magnetic field. Our developed die has two sensitive directions, X and Y axes. However, only one is used in this work. As for the cilia, it is made as a cylinder composed of a mixture of neodymium iron-boron magnetic particles with a PDMS polymeric matrix at a proportion of 65% magnetic particles to 35% PDMS in mass. The particle magnetization is oriented in the cilia axial direction, which will induce a permanent magnetic field within the cilia and the surrounding space. When the cilia bends, this magnetic field will change, thus inducing a variation on the signal of the magnetic sensor underneath. Variation in magnetic field is monotonic. and therefore has a one-to-one correspondence between cilia deformation and signal, thus allowing our device to measure surface topography and texture. In this demonstration, you can see the sensor being actuated. As the user touches the cilia, the corresponding deflection is measured in real time. The sensor has a data acquisition rate of up to 1000 samples per second and a resolution of 24 bits. The cilia are made using a master mold technique and therefore are easily interchangeable. 3 configurations were tested for this work. One using a single 3 mm high by 400 micrometer diameter cilia, another using a 3 by 3 cilia matrix with 1.6 mm high and 320 micrometer diameter, and another using the same 3 by 3 cilia matrix with 3 mm high and 400 micrometer diameter cilia. This device was attached to a Geomagic Touch haptic interface, programmed as a robotic arm, which will perform the movement of the sensor on the fruit. An Arduino communicates with the cilia sensor and serves as its PC interface. The fruit under test is placed on a vise to hold it still during testing. The experiment is performed automatically for each type of fruit. For this work, the goal was to provide a binary classification in what concerns the quality of the fruit, that is, if the piece of fruit is rotten or ripe. As such, the device cannot classify what kind of fruit is being tested. The classification algorithms are trained independently for each type of fruit. 2 types of fruit were tested: strawberries of the Sabrina variety and apples of the Braeburn variety. For each type of fruit, 12 ripe and 12 rotten fruits were tested. For strawberries, senescence was achieved naturally, while for apples, due to their long conservation time, the senescence was cold triggered by placing them at a temperature of minus 18 degrees Celsius for 24 hours. The test sequence is performed in 4 steps. First, the robotic arm lowers the cilia against the fruit until it makes contact with it. This is performed automatically, using a threshold. Then, the arm makes a fast movement to orient the cilia in the sensitive direction of the sensor. The stand begins afterwards and is performed at a constant velocity of 100 micrometers per second. Finally, the arm returns to its initial position. This cycle is repeated 10 times for each fruit. 3 features are extracted from the fruit scan, each corresponding to one of the fruit tactile features. Stiffness is estimated by taking the average value of the first 100 signal points, as the initial deflection of the cilia against the fruit will depend mainly on its firmness. Waviness is the low-frequency behavior of the surface texture. It is estimated by low-pass filtering the signal using a 1000-point moving average and taking its standard deviation. Roughness, on the other hand, uses a high-pass filter to eliminate frequencies below 120 Hz and taking the standard deviation of the resulting signal. 2 classification methods were employed: Gaussian naive Bayes classifier and a random forest classifier using 100 classification trees. These methods were chosen as they allow the usage of Bayesian updating, as more scans on the fruits are performed. Validation was performed using a leave one out cross-validation method. For the Gaussian naive Bayes, it was assumed that, statistically, the features can be described by a trivariate Gaussian distribution. Using the training fruit data to estimate the mean vector and covariance matrix of each fruit class. The quality of the classified fruit can be estimated by taking the conditional probability of the test fruit belonging to a certain quality of fruit. The probability is updated with each performed scan. The classification decision is made using a maximum a posteriori estimate, that is, by choosing the class with higher probability. An equiprobability prior was used in the classification. On the random forest classifier, an ensemble of classification trees was trained with the training fruit data and expected responses. Each tree computes a prediction given a certain data point. The classification decision is made based on what the majority of classification trees classify the data as. We use the ratio of trees choosing a certain class of fruit for a given data point divided by the total number of trees as a probability estimation of the fruit under test belonging to a certain class. With this probability, a Bayesian update can be made, as more scans are performed in the tested fruit. The validation and accuracy assessment was made using a leave one out cross-validation method. From the data measured for all fruits, the data for one fruit was left out for validation, while the remaining data was used for training. The validation result is taken, and another fruit data is selected as the validation set. This is repeated until all fruits have been used as the validation data. Finally, the accuracy is taken as the sum of true positives, that is, ripe fruits classified as ripe, and true negatives, that is, rotten fruits classified as rotten, divided by the total number of tested fruits. All the combinations of the three configurations of sensors with both fruits were tested. In this slide, the accuracy after the 10 scans are performed is shown. In general, apple classification achieved higher accuracies than strawberry testing, with the best overall performance occurring for the case where the single cilium sensor was used for testing apples, reaching an accuracy of 96%. However, when testing strawberries, configuration C cilia showed the best performance, with 83% of accuracy. We hypothesize that this is due to the larger area of contact of configuration C. When using a sensor with higher spatial resolution, that is, lower contact area, any bumps on top of the surface will be accounted by the classification algorithm. This is beneficial for smooth fruits, such as the apple, but not naturally bumpy fruits, such as a strawberry. By using a higher contact surface, the result of the measurement will be averaged over the whole contact area, limiting the effect of existing bumps. Furthermore, accuracies do not differ substantially between both algorithms, revealing that good results can be achieved by this sensor mainly due to its capability of collecting relevant data, regardless of the used classification method. For the most accurate classification cases, as seen in the previous slide, apples measured with configuration A cilia and strawberries measured with configuration C cilia, the number of misclassified fruits tends monotonically to lower values, with an increasing number of scans, when using the random forest algorithm. Furthermore, the best performing Gaussian naive Bayes classification reached the minimum error in 7 scans, while it only took 3 scans to achieve the minimum error with the random forest classification. This means that the classification takes less than the 10 scans taken initially to accurately classify a fruit, given that the right combination of cilia configuration is used for each fruit. Finally, the influence of the number of features used to train the classification algorithm versus its performance was studied. It can be seen that, for both classifiers, the accuracy increases with the number of parameters, meaning that all extracted features have some amount of information about fruit quality. However, when using 3 features, there is only a marginal increase in accuracy over using 2 features, while there is a great improvement when using 2 features instead of only 1. We have developed the cilia-inspired tactile sensor that has the capability of measuring and resolving very small forces and textures. The device was implemented with a robotic arm as an automatic fruit quality detection system, using the fruit surface characteristics as parameters for classifying fruit quality. 2 fruits were tested, apples and strawberries, with the maximum accuracy in classification being observed for apples with a 96% accuracy. However, the exact accuracy varied depending on the number and size of cilia used and the type of fruit being tested. For future work, we will be using a 2D magnetic sensor which should be capable of measuring cilia deflection and tilting angle at the same time. We will classify the fruit into more classes instead of just ripe or rotten in order to assess the fruit quality in various degrees. Finally, we will attempt to implement this device in an agricultural machine or industrial fruit processing line. Thank you.